off on, was there? Yes.
On section 2.4, it was one of the stem and leaf plots. I think it was the one number 89.
That's a good problem. I love that problem.
I
know. I know. Normally, problems I love are those are the ones you got to be careful with.
Yeah.
Zoom in, and then we can talk about the questions it asks. Okay. So part A is pretty, describe the shape of the box plot, and you can actually describe. Now, the immediate thing I would think, this is ages of people that bought these cars. So to me, I would immediately describe them in terms of what they mean physically. I was trying to figure out what the book might intend, because later they ask you directly what are the ages of the people that buy this, and that's the way I would describe this. Which car seems to be bought more often by younger people? The 3 So that's the way I would describe the distribution. Now you could say the data are clumped at lower values for the BMW 3 and make it a little less physical and more just shape-wise. And these two are very, very similar. Just the median is a little bigger on this one. Right, slightly older people, but then I'm bringing the ages back in. To me, I want to tell physically what the hell does this mean. So part A, you can answer it a few different ways. Part B, so what part of that did you have the most trouble with? Do you remember?
I remember I kind of had problems with F through H.
Oh yeah. Oh shoot, where am I facing? I'm facing wrong. The interquartile range. We didn't talk about that, but it's just a formula. What is the interquartile range? What are the interquartiles would actually be?
Quartile 1, quartile 3.
Q3, Q1, I like it. Q2 is like the middle, so the inner quartile range is Q3 minus Q1. And that would be the box on the box and whisker, right? That's basically how wide this is, isn't it? Because that's Q3 and that's Q1. So it's like, where is your middle 50%? Where's the heart lie at, right? You can talk about it like that. So that's part F. Is just look at the BMW 5 Series, estimate the interquartile range. So it's just looking and estimating what's this minus this. That's the interquartile range. Okay, so the range is high minus low. The interquartile range just takes 1/4 step in. What's Q3 to Q1? What's that distance? Yes, sir.
No, I'm not sure. I had a question. Like for discrepancies in this, like say a 70-year-old or whatever, a 50-year-old is going to buy the 3 Series for his 25. How do they like figure that out? Or
well, now you're getting deeper into what were they trying to say, and did they capture the data correctly for what they're trying to say? So you're talking about if they're trying to say intended users of the car. If they're trying to say something about the users of the car, then that's one thing. But this is talking about the buyers of the car. Who gives a crap what they do after that? I just care about who's coming in to buy these things. If they want to give it to their daughter, or they want to give it to the next door neighbor or whatever, fine. Does that make sense?
Yeah.
So I'm talking about what are my people that come in and actually buy the damn cars, and as a seller, that's who I care about. You do whatever you want to with the car. You with me? But it's a good point. If you're trying to say something about the people that drive the car, then the way they collect the data might not be right. They didn't really address that. That's a good point. But that's going a little deeper than we need to. Yeah. Part G says, now this is where things get more interesting. Look at the BMW. They ask you to look at the BMW 5 Series over and over and over. Are there more data from 31 to 38? From 31 to 38 than there is from 45 to 55. 45 to 55. How do you know?
45.
Yeah, where would there be possibly more data?
And where it's come together? In the middle.
More than likely, because what percentage of the data is here?
25.
Only 25%. What percent of the data is in here?
50.
And what percentage of the data is in here, though?
25.
25. So that's where this problem gets interesting. So 31 to 38, 45 to 55, 45 to 55. So think about it. How much data is in here?
25%.
So between these two, what do you think it's 25% still? Probably less, right? I know what they mean by this problem, but there's too much unknown here. So if I had to guess, I'd say here actually, there's definitely 25% from 31 to here, right? Yeah. Definitely. And did I say 31 to 38? Yeah, 31 to 38. There's definitely 25%. But here, from 45 to 55, there very easily could be less than 25%. I don't know if you guys see that. How much is there from Q2 to Q3? Between every quarter, there's 25%. That's why it makes sense that we call them quartiles, quarter. So weirdly enough, there'd be more data there, more than likely. That's the kind of thing you got to think about with a couple of those last questions on that problem, right? Same thing with that part H. It's pretty much exactly the same idea. Yeah. Freaky, freaky. Any other questions? So if that's the only one you have trouble with, you're doing great. I mean, that one really forced you to analyze the hell out of these box plots, which is good. You got to go through that at least once in life. Builds character. Anything else from homework? Is that cool? Yes?
What did the line box plot thing mean? Just when it's just a straight line?
Oh, that means there's a lot of repeats in your data. So if I had data that looked like this, 2, 4, 4, 4, 4, 4, 4, 4, 4, 4. What's the low? 2. What's the high? 4. And what do you think Q1, Q2, and Q3 are? 4. So there'll be a low, there'll be a high, there's a Q1, Q2, Q3. So then when you draw it, oh well. So we saw that real quick the other day. If there's a lot of repeats, or there's very few data point options, then you could have at least a couple of lines overlap, if not a whole bunch of them overlap. Obviously, if the whole data was that, what if the data was that? Then they'd be like, so it doesn't go anywhere. It's got no variation. Yes?
For the question where it's asking like China, Germany, and the United States, how many people visit what countries? For China, it's 0 and 5. How would you, like, ask you to explain that? How would you put that in the numbers? Which is a lot of repeats at 0 and 5.
Well, where was that? Shoot.
Number 86.
So like 3 of.
All right, okay. Let's see. So what are we saying here? Describe what the shape of each box plot implies about the distribution of data collected. So China, what do you think happens with China? Basically what we just said, right? Now we don't know if there's a whole bunch of 0 or a whole bunch of 5 or like equal amounts of 0 and 5, but pretty much there's got to be just 0s and 5s, right? Either people have been to, what was it about how many countries they've gone to?
Yeah.
Either they've been to no other countries or 5 other countries, pretty much. With me? Okay. But what was it specifically? What's going on with Germany? What do they use a dotted line for? And this is not a general thing. This is just this book does it. The median. I like it. So we just put lines like we're supposed to. So what was the trouble? Let's see. Have more Americans or more Germans now? No.
No, I was just wondering how you would explain that. You just say that they're either 0 or 5.
Yes, that's the best we can determine. There might be like one other data point that just happened to not become a Q1 or Q2 or Q3. But there were so many repeats, so there's not a lot of variation in the data points themselves. Does that make sense? Yeah. There's a lot of repeats of something. That's how it would end up looking like that. Right? No box, just whiskers. Right? Just this whisker thing. No cat, just whiskers. Walking around the house. That's weird. Okay. Yes?
Number 80 is asking you to use convenience or like what type
Oh, okay, sure. Oh. So the data were collected by asking the first 111 people who entered the store. Then the type of sampling is what? Yeah. Yeah. What's up? Is that all right?
No, I just wanted it.
Yeah, they didn't have a system to it. They didn't break people into groups, so it's not cluster or stratified, right? They didn't have a system. It's not. They didn't even give us the option of systematic. It's not simple random. They had no. They did nothing to random. They just said first on let people I see. So why would that necessarily be bad?
Bias.
Why? Why could it be biased?
Be everyone coming from one, like,
They all shop at the same store.
Yeah.
in the same group, like the same.
But maybe they only want to talk about their own store, so that's all right.
Everyone on lunch break in the same office.
Exactly. Well, it depends on when they open, right? They open up at 9. If they have a lot of people come, then they only get the people that are out early, right? And for those of us who are not out early, we're like, well, shit, that's not fair. I want to have a say in this too, right? So, I mean, this kind of question you can ask, well, how could they do better and so forth. There was another problem like the airline problem. I think that was how can you do better. So obviously I would take throughout the day, depending on what I want to say, maybe other stores, stuff like that. All right, but it's possible they want to just talk about their own store. So it doesn't matter if they just take customers of their own because they just want to know about themselves. All right, screw the other. Yes, ma'am.
Section 2.7, number 95.
Oh, good. Yeah. All right. So pretty much, if you draw this, can you draw the box plot for this? Well, not totally, but because I don't know what the low and the high were, right? But I know the median is 1,014, right? I know that the first quartile is 528. I'm not even going to make a scale because it's just a rough sketch, just so I have something to look at. Third quartile is 1447.5. And make sure you really, really understand. This is not good to turn into me. This is bullshit. But this is just me. It's not asking me to draw it. I'm just drawing it for myself. It's just a quick visual. So that's the first. So this is like the box. And I don't know where the whiskers are because they don't tell me. All right, so who knows? 75% of all years have an FDS at or below. So where would 75% of the data be? Below what? In general, 75% is below what? I don't know if you understand. It's like, what percentage of the data is below Q2? By definition, it's 50%. It's the second quarter of the data. So it's 50% below, 50% below. So which thing has 75% below it? Which thing?
The Q3.
Q3. What's the third quarter? How far into the game am I? If I just finished the third quarter, 75% of the damn way in, right? Got 1/4 of it left. You with me? So at or below, so which value is the third quartile? Well, it's this one. And that makes sense. There's 75% below it. Now, which one has 75% above it? It must be the one that has what below it? 75% above means 25% below, so that would be Q1. You don't really need the picture, but anyway. Does that make sense?
Yes.
So when you first read through that, it looks weird, but why did they pick 75%? Because it's exactly related to the quartiles. And that's the only thing you really know. Okay. Yes, sir.
Just a quick question. So, like, on the homework, do you expect us to, like, write the entire question out and then, like...
No. Yeah, I have the questions. You don't have to tell me the questions. If you're somebody who likes to write the question, you can, but I don't need them. Thankfully, I have a book, so I know the questions. I like when people write the whole question down and then they don't put any answer. I'm like, I'm going to give you credit just for writing the question? That's right. So I'm not. I know you weren't going to do that, but it's just funny to me. Yes? This here? B? Where'd you go there? So how did you do part A?
40 times 29.
Yeah, so 40%, yeah, 0.4 times 29, and then you rounded that up and took that answer.
Exactly.
All right, do the same exact thing with part B.
I did, but it gave me a 69, but it's 70.
The book uses a slightly different way to do it, which is just a different way. So I agree with 69. Because you did And I think it might have been a typo, to be honest, because even if you do it a different way, it doesn't come out to that. But I think it's just a typo. The 78%, 0.78 times 29 comes out to be 22 point something, right?
22.62.
So you round it 23rd. The 23rd number is the answer. You go to the 23rd number, you're done. Right? So I think it's just a typo, to be honest. Right. Right. I thought people had trouble with this one. This problem, they have a really gross-looking formula for this. To be honest, that's one option. And the reason that gross formula exists is to take care if there's more than one of the number, you want to kind of adjust for that. But with a small set of data like this, there's no reason to be that precise. Just count up to the number the first time you see it if there's a repeat, and then divide by the total number. And that's a good estimate for the percentile. If you have a large set of data, then it's going to naturally wash out to be more precise just because there's a lot more data points and they can each be their own percentile. Small set of data, what point is there to be precise? I don't know if that's making sense. So if you want to use a formula in the book, totally feel free. You don't have to. Just count up to the number and then divide that by how many there are. That's how far you went into the list to get there. It's a good approximation for the percentile.
Okay, so the same question. You don't have to count in 12 and then count in 12 and then do the hypothetically 21% over 2. So
for this question here?
And let's do 20 groups. Do 20 groups. Find the 40th percentile.
Oh, find the 40th percentile.
Yeah, just do that one. So then it comes out to 12 for the answer. It's 11.
Okay, because you round it up, okay?
To 12.
So you take the 12th number and you're done.
Okay, but then what am I talking about from the notes? You went 12 in from Q1 would be 25% of the way from the bottom. Okay. So if Q1, if I have to step in 12 times to get there, that's the Q3 would be 25% of the way in from the top. So I could just count 12 from the top. That's a shortcut. That's just a shortcut. So if it doesn't make sense, don't do it. Yeah. But that's what I'm saying. You can do it if it's a shortcut, right?
But here it doesn't apply. This is not a quartile. There's no shortcut. Yeah. I mean, second.
So when would it apply?
When you have an equal amount from the top and an equal amount from the bottom. So if you find P40 and you know it's 12 steps in, if they ask for P60, then it's 12 steps from the top in.
Oh, I see what you're saying.
They're equal.
Okay.
Yeah, good.
Okay.
So for that shortcut to work, you got to have the symmetric situation.
Got it.
If that makes sense.
Yes. Thank you.
Okay, good. I like that. All right. We got a lot to do. That's plenty of questions. Okay, good. So I want to finish up that handout from last time. You have it up here, Jeff. Good. So if you remember last time, we did this. We stared at a blank screen back. We got these numbers by doing that handout. Somebody need that handout? I only have a couple here left. And that handout is this handout here. There. No. Oh, it's frozen. Unfreeze. All right. This one. Anybody need that from last time? Hopefully not more than 2 of you. I think that looks like 2 of you. Good. Thank God. All right. Oh, you got it? Cool. All right. Sweet. All kinds of stuff going on there. There's some calculus. Calculus stuff there. All right, so we did this procedure with different data, right? And we ended up with, when we did it, we got a variance. I can't remember. But the standard deviation we got was 3.177.
3.07. Oh, yeah. Sure.
Cool. And the mean we got was 5 point, I think I told you to round to
2 decimal places, right? 5.69?
Yeah.
Sickle. So, let me ask some of these same questions. How many standard deviations from the mean? All right. So now watch this. If I had a data point of x equal to 10, let's say, how many of these do I need to go from here to there? Is it like one of these? So if I start at 5.69 and I call these steps very often, right? And the reason is, let me talk about this in a more general way. So if I had an average of 20, but my standard deviation was 0.2, wouldn't that be very tiny? I mean, it wouldn't get very far away. It would be kind of compact, right? So I call my mean was 20, but my standard deviation was 8. Now it's more spread out, right? It goes up and down. On average, every data point is 8 away from the middle, so it's more spread out. You with me? So I think of standard deviations as steps. So if I'm in my data, can you imagine my data is on the ground? It's a little mound of data down there, right? And I want to step around my data, and it's really tight. It doesn't vary much. Then I'm going to take little tiny steps. Oh, right? I don't know if you guys are with me or not. You guys are all like, God, this guy just went insane. But it's sort of like if you wanted to measure the distance between 2 atoms, or measure the distance, how the radius of the electron orbiting the nucleus, right? Oh shit, Jeff, where are you going? Is that very far? You're not going to use gigantic. You're not going to use miles. That would be an insane unit to use. So my standard deviation is sort of like saying, do I want to use inches or kilometers, or do I want to use nanometers for like stupid small, femtometers for really stupid small, gigameters, stupid big. I don't know, you guys kind of with me? Yeah. So deciding on, if I said how far is it from here to the nearest town, and you told me some number of inches, I'm going to slowly walk away from you. Right? So like your mom saying, oh, he's 3,872 months old. Shut up. Thankfully, she doesn't do that. All right, you guys kind of with me. So standard deviation sets up which side of the ruler I'm using in a way. Do I want to use the centimeters or the inches, or even do I want to go beyond that? Do I want to use some big ass things? And then what I want to do now is I want to lay that ruler down and measure how far away a data point is. So if I have the 5.69 as my mean, and 3.177 is my tick marks on my ruler, they're all 3.177. Can you guys see that it would definitely, up to 10 would be more than one step, of course, right? Because how far would I get with one step? From one step up. My steps are that big. Where would I go to? Well, what are we? 8.86 roughly. 8.6. 8 point. What is it?
8.86.
8.86. Thank you. Is everybody cool with me right now? Yeah. So here's the mean. If I want one step, one standard deviation up, I would end up at 8.86. So if I wanted to estimate, I'd say this is like, I don't know, 1.5, less than 1.5 steps away. One step up is 8.86. Another full step up would get to 11 point something, right? So it's less than 2 steps away, but it's more than 1 step away. So how do I figure out exactly how many standard deviations away it is? Exactly how many standard deviations away is 10 from this? Well, how far apart are they, period? You subtract 10 minus that, and you want to see how many standard deviations fit into that. It feels a lot like class width. You would take 10 minus 5.69 divided by how big each step is. So if I had to go 8 feet, and every step I took was 2 feet big, how many steps would I take? 4. 8 divided by 2, I take 4 steps. So I want to go this far. Every step I take is this big. So how many steps would I take?
1.36.
1.36, I like it. So a little less than 1.5 steps, which is kind of like jiving with what we thought it would be, just to estimate it. So that, tell me again, what does that number mean?
many standard deviations you are from the mean?
The number of standard deviations from the mean to that data point. Oh shit. Do you see how slow I said that compared to how I normally talk? When I slow down, that's a key. Note. That's a note. That's a note.
You say it wrong now.
Yes.
Yeah.
In fact, I'll make it a little more specific. We call this a z-score. So a z-score tells you the number of standard deviations from the mean to a data point. All right. So this work I did, is everybody cool? Got that? Let me just tell you this. Every single test I give you, I will ask you. Do you understand what's happening right now? I am telling you exactly what's going to be on a test. I'm going to ask you either, what does the z-score tell you? That. Or I'm going to ask you, if I had a z-score of 3, what would that mean? That would mean that data point is 3 standard deviations above the mean in this case. You can be more precise. Positive z-score is above the mean. Negative is below the mean. Does that make sense? Because when I subtract the data point minus the mean, it's going to come out to be negative if it's below the mean. So here's the formula for z-score. You ready? Formula for z-score. There's a reason I put this on the overhead, not for this. So in general, the z-score is the data point that I'm interested in minus the mean divided by the standard deviation. So my standard deviation came out skinny that time. This is for a what? Who can tell because of the letters I used? That is for a what? Population. Kick ass. If I want to say for a sample, it would be x minus that mean divided by that standard deviation. So it's the same stupid formula, right? Same formula, different symbols. So if I have a population, I just use the symbols mu and sigma. If I have a sample, I use the symbols x bar and s. Is the formula different? No, formula doesn't give a shit. It says put the mean here, put the standard deviation there, whatever they are in this situation. How we doing? In fact, the z-score formula never changes. In about 9 weeks from now, there will be several of you that don't believe me, but I don't care. I'm going to try to make you understand that it's true. It never changes. That's for example. So let's come back to this handout. I want to answer some of these same questions for the data we did last time. So we just did one like this. We just did one, how many standard deviations from the mean to the point 10. We figured that out to be a z-score of, what do we say? 1.36. So I can ask you that kind of question. The homework asks you that kind of question, section 2.7. This one is more interesting now, and this one's going to lead directly into some neat theorems. So if I put the mean, so what mean did we figure out from our data? We found the mean was, where do you go? 5.69, right? From the data we did the other day. Yes, not yesterday. If I take one step up, we just did that a second ago. We got to 8.86, right? Remember that? If I take one, so if I take an x bar and I add one standard deviation. Is that cool, that terminology? Start at the mean and go up one standard deviation. Go up one step from the mean. Now do the same thing in the other direction. Where do you end up? So subtract. What are you subtracting from the mean? You're subtracting one standard deviation, so you're taking 5.69 minus 3.177. $2.513. See? Okay. All right, you guys still with me? So, if I take one step up and one step down, and the standard deviation is the average distance from the mean to each data point, I could possibly collect some data in there, right? They only get, on average, they get that far away from the middle. How are we doing so far? Yes, sir.
How'd you get the 15 though? The plus and the minus.
Oh, it's not. It's an S for standard deviation. Plus or minus. Let me put SD. Is that cool?
Oh, okay.
One standard deviation up and one standard deviation down. So that's what I mean when I say within one standard deviation. If I said guess my weight to within 10 pounds, I'd let you go above by 10 and below by 10, right? So within means both directions. Okay, cool. So what was the list of data? Let me see. I think I still have it here. I don't know if you still have that data list. All right. If you still have the data list, how many data points fall in there? So like the number 2. If I see data point 2, is it in there? No, it's down here, isn't it? So what data points are in here? 3, 4's in there, 5's in there, 6, 7, is 8 in there?
Yes.
Yes, and then 9's out here, right? So how many of these do I have in my data?
1, 2, 3, 4, 5, 6, 7, 8, 9.
No, I like it. And how many total data points did I have? 16, right? So what percentage of the data is in here? 9 divided by 16. So we're doing the exact same work that I did up here, right? For that example. Who's it? 56.3%. So over half the data is within one standard deviation, which makes some sense. It actually doesn't have to be something like that, but sure. Yeah. So we start to see what the standard deviation does for me and how I can start to use the standard deviation. So if my data was more spread out, my standard deviation would get bigger. So I would still kind of step out and catch so much data. So let's talk more specifically about that. There's a very neat theorem